Okay, so now we had this BCD to XS3 code converter, and we have the input. What is the input? BCD. What's the output? XS3. We add 3 to it. Okay, now we can also have another problem. In exam, I may also give you the same question, and this can also be a question of exam. This can also be a question of exam. Design a hex to XS3 code converter. So hex to XS3. So now you need to know hex, the hex incrementer. Got it? So there can be like the questions can be different. So now we have, when we have some problem, so we do the formulation. How can we do formulation? By drawing the truth table. Now we draw the truth table. You know how to draw the truth table? Yes. Now we got 4 functions. What are these 4 functions? W, X, Y, and Z. And then we did some chem maps. Can you see? If you look at W, how many ones? 5. So there are 5 ones in the chem maps. How many don't care? 6. 6 don't care in the chem map. Please remember, I will not going to repeat the chem maps again and again. And these chem maps will be used all everywhere. So this may also be a question of exam. I will give you the question. Design a BCD to XS3 code converter. And then you need to formulate the problem. You need to draw the truth table. From that truth table, you have 4 outputs. From that 4 output, you need to draw individually 4 Carnot maps. From this truth table, you draw. So this Carnot map is the Carnot map for which variable? W. And please do it at home. This may be a question of second midterm. I'm telling you. And I will give 1 or 2 questions for my lecture slides. Exactly same. It's up to you to practice or not practice, up to you. This is like just a hint. From the slide, 2 questions will be from the slides. 2 questions can be from the slide. And I'll also give you the practice questions in the exam. So that's up to you. If you want to solve it, no solve it, it's up to you. Now X, how many ones in X? 5. How many don't care? 6. Then Y, and then Z. Now, if we did it, what should be the next step now? What should be the next step? We draw the Carnot map. How many functions do we have? 4 functions. Each function of how many variables? 4 variables. What do we do? Logic minimization. So we do the grouping. Okay, we start with the largest grouping. Now we derive some expression for variable what? W. This is the expression for variable W. This is the expression for what variable? X. Then Y. Then what? Z. Got it? Why we have reduced expression for Z? Why do we have reduced expression for Z? Because we have combined don't care with Z. We have combined don't care with Z. So now we got 4 functions, and each functions is implemented using. So now this is the formulation. We formulate the problem. Now can you see here? Now there is some observation, and this is very important topic. Did we cover this, or I'm going to repeat it? Yes. I know, but I want to record so that you know. Hello. Okay. Now good. Can you see here? How many functions do we have? How many functions? 4 functions. Now we have 4 functions. What are the name of these functions? W, X, Y, and Z. Now can you look at W? Please look at W and think of that. So now if you look at W, so W is implemented something like this. So W is implemented like this. So we need an OR gate. How many input OR gate? 3 input OR gate. What is the first input? A. What is the second input? B, C. And the third input? B and D. And this is W. Okay, now we have X. Okay, if you look at X, so now we have another OR gate. How many inputs? 3 input OR gate. And now 3 input OR gate, and then we have 2 AND gates. One is B bar C, and then which one is B bar D, and the other is B C bar D bar. So this is expression for what? X. For Y, can you see here? For Y we have this circuit. Got it? And what is the circuit for Z? D and DCC. Got it? Okay, now this is the circuit. And now please look at here what we are going to. Is this an optimized circuit or unoptimized circuit? Why optimized? Now we have reduced it. We have reduced it. Why it is unoptimized? No, we have now. This is a question. This is a question. Please, now we want to. Yes, can you answer me? We did Carnap map. Okay. From Carnap map, we have derived the reduced expression. Please answer me. Anyone, answer me. Is it efficient or still inefficient? Why it's still inefficient? Yes, very good. Now that's the answer. We need to find some opportunities for logic sharing. So now we need to. Why we need logic sharing here? Why we need logic sharing here? Because now we have 4 functions and we need to find some opportunities for logic sharing. Please look at all the expression. All the expression. How can we exploit logic sharing? Look at all the expression. Yes, please. Okay. Now we do some magic. We do some magic. Okay. Can we write it like this? Same thing. Can we write something like this? Got it? Now please look at the observation. There is some color coding. In that color coding, what's your observation? Which color is more prominent? Red or blue? Red. What opportunity is in red? Common term. What is the common term? C plus D. That's the thing. So whenever we derive some expression, we can further do some, okay, which method is this? In the first method, we use Carnap map. From the Carnap map, we deduce the minimized function. We extract the minimized function. But what we are doing now? Which procedure we are doing? Now we are doing something. Logic sharing, but which method we are using? Algebraic manipulation. You got it? Though we did Carnap map, we said, okay, Carnap map is a good technique. Carnap map will give us the derived expression. But now, once we get the reduced expression, we need to do some large algebraic manipulation. Use all of the theorems. You can use De Morgan theorem. You can use all the theorems, and then you deduce. So from that expression, if you look at this BC, then we do some magic, and from that magic we see, okay, now there are some room for things. Now, if you look at the blue thingy, we can also use De Morgan theorem. Again, find some more room for optimization. There is another room for optimization. What is your observation now? We have transformed this C bar D bar, which is in blue color, and then we have used De Morgan's theorem and C plus D whole bar. Now, what is now the common term? C plus D bar. So this is now the common term. So now you did. So I will give you a lot of questions especially for the homework. I will give you some challenging question, and you need to find opportunities. I will not give this kind of hard question in the exam, but I will give you this question for the homework to make you prepare. And I have already checked most of the midterm. And what's the problem for majority of the students? What they do, they don't practice. I'm telling you, that's the only problem. I asked very simple questions. And when I saw some of the answer of some of the students, they were very naive. It means that you didn't try homework. Some of the students who had bad grades, they didn't try this at home. So this is my recommendation for the next midterm. For the next midterm, I will ask 2 questions exactly the same from my slides. Please go through all the slides again. Got it? Okay, now what is another room for optimization in this expression? Yes, please. What should we do? C bar D bar can be again C plus D. Again, we transform this into form of. Okay, now how many times C plus D is used here? 1, 2, 3, 4, and 5. This called is logic sharing. Now you are using NZ is D bar. The C plus D is the common term. And if you deduce the expression for all these things. Okay, now please look at here. And now this is a very tricky question. Just look at all the diagrams. Just look at, and I want your observation here. Just now we did something. How many gates here? Excluding the inverters. I'm not including the inverter. How many gates? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many gates here? 1, 2, 3, 4, 5, 6, 7, 8. Inverters, I'm not excluding the inverter. So okay, if you look at here, there is another observation. Here, what is the size of the OR gate? 3 input or 2 input? 3 input. If you look at all the OR gates, 2 input or 3 input? 2 input. So now you know what is the advantage of logic sharing. There is also a room for optimization, and in this room for optimization, and if you look at here, how many times C plus D has been used? 5. 1, 2, 3, 4, and 5. Yes. Here, here, here. Yes, please.
For C plus D bar, it's the same.
So C plus D, can you see? This is C plus D, and this is C plus D whole bar. And now, how do we do deduce the expression? So if you look at deduced expression, now what is this? B. Then you remember, this is what? C plus D. This is C plus D, and C plus D goes there, up. What is this? B dot C plus D. And what is the expression for W? The same, the same. Now it's B bar, then what? B bar C plus D, and then this B, this C plus D whole bar. Now can you see C plus D, then it becomes C plus D whole bar. And then we use the gate level minimization, and now this is the expression for X. Similarly, this is C plus D whole bar, this CD whole bar, this one is this expression, and now. Okay, now from the first method, when we use Carnot map, we use Carnot map. From using the Carnot map, we derive a reduced expression, and that reduced expression was in the sum of the product expression. But since we have one function or multiple function of the same inputs, multiple function, how many functions were of the same inputs? 4 different functions of the same input. Then we find opportunities for common terms. We did some algebraic manipulation, did some magic, and it was there in the slides. You can also do this magic on that. So you do this algebraic manipulation, extract some common terms, and you further reduce your cost. And in this problem, if you look at here, we have reduced the size of the OR gate. We have also reduced the number of gates. So these are the advantages that we achieve using. And this method is called, which method is called as, which method? Logic sharing. Now, this is one method. The previous example was method number 1. Okay, now still, if you look at the previous slide, now in this slide, look at this slide. So in all of the implementation, okay, now in this example, it was designed, this W was designed in isolation, X was designed in isolation, Y was designed in isolation, and Z was designed in isolation. But in this example, isolated or combined? Combined. So this is called as the isolated optimization, and this is called as the joint optimization. What's the joint optimization? In joint optimization, we identify the common terms and use these common terms. So this is the joint optimization. Okay, now if you look at both of these approaches, this approach and this approach, what are the type of gates? Which gates we are using? Only 3 type of gates are used. And are inverted. Which logic? SOP. Some of them. We can also do the same kind of optimization in the product of the sum. So you okay, now for that Carnot map, we use the SOP expression. We can also use the POS expression, and from that POS expression, we further identify the simplification, and you can do it for that approach as well. Any question? Should we proceed? Okay. Now in another slide, now in the next slide, what we are doing, we are using another approach. We call this as the mixed gate approach. So now this is thing. Can we write something like this? Can you see? What is this? A plus B, C plus D. C plus D bar is the common term. Can we say, what is C plus D? We say, oh, C plus D is P. So can we say P bar P plus B? P bar. Which gate? XOR. Can we say B exclusive OR P, and P is actually C plus D. Got it? And this is C. What is this? We further this. Can you do it something like this? Okay. So this is D bar. So if you look at here, so now which design is this? Which design? Which approach? No, which approach is this? We do also the logic sharing approach. We combine a lot, but this is called as a mixed gate approach. Yes, please.
What's up for the second one?
Which second one?
For Y.
Why? Yes.
Can we do C or D or
Whatever you do is something like. But this is the most optimized approach, because you know this kind of optimization is done with a lot of thinking. It's not. It will take a lot of time, just like to write a complex program. So when you have some, if you have some more optimized approach than this approach, please come with that. Got it? So I will give you bonus mark if your mixed case approach is better than this approach. There can be a lot of ways that you can do it.
What is the D bar?
Which D bar?
For the Y. Does it have to be bar or can it be normal?
No, no, we say D. I say, which one?
The third, yeah, this one.
Yeah.
Isn't it supposed to be C or
Up to you. It's up to, just renaming something. So we say, what is this D bar? Can I call this as P? Just like for my understanding. I say P is equal to D bar. When we have this expression, so we can say CP bar plus C bar P. So you can say C is exclusive or P, and P is nothing but D bar. This is just like how to interpret it. This, and then we do deduce all these expression. So can you see here, what is this B? What is this? C plus D. And what is the expression for X? X is equal to B exclusive or C plus D. So now if you want to have an optimized expression, come with your own. Come your own. Okay. Now what about X? This is X. What is Y? This is Y. And then we can have. Okay. Now we had two approaches. We deduce the sum of the product expression for each variable w, x, y, and z. Then we identify some common terms. We exploited that common term and then do some logic sharing approach. Now in this method, okay, this method also requires some knowledge. What is that knowledge? You should use what? Algebraic manipulation. So you do algebraic manipulation in an efficient way to identify the common term and transform this into some combination of exclusive OR and exclusive NOR gates, and then we did. So now this is how we derive this expression. Okay, now what is the last step, which is called as the verification? We did a lot of examples. What was the first step? Specification. Specification takes have a real world problem. What can be the specification? I told you in the last lecture. Design a BCD incrementer. Design an XX3 incrementer. It can be a specification. Okay. Now, after that, we draw the truth table. From truth table, we did what? Carnap map approach. From Carnap map, we derive reduced expression. From that reduced expression, we did identify common terms, and then we do the optimization. And the other approach, we also do the algebraic manipulation and then transform it into a mixed gate level approach. And in the final step, we do the verification. We apply all of the possible input patterns and see whether the output is correct or incorrect. How many possible combinations will for A, B, C, and D? How many possible combinations? 16. So we apply 0, 0, 0 and see what is W, X, and Y, and Z. Okay, so now please look at here. If we apply 0, 0, 0, 0 here, what should be the output? 3. Because BC2 X is 3. If I apply 0, 1, 0, 1, 1, 0, 0. If I apply 0, 1, 0, 1, 1, 0, 0. 0, 1, 0, 0, what will be the output? 0, 1, 1, 1, because it's ABCD. So you apply all the inputs. So if the input is 0, 0, 0, 0, the output should be what? 0, 0. Okay, please look at here. 0, 0. This input is 0. This input is 0. W is what? 0. 0, 0. This 0, 0. Okay, now this is 0. C is 0. 0, 0, 0, 0. It is also 0. 0, 0. And X should be 1. C is 0. D becomes what? 1. It will become what? 1. And when exclusive or 0? 1. The output is 0, 0, 1, 1. You got it? So this is, you apply all of the possible combination. This step is called what? Verification. And this verification you also do it in your programming. You write some code, then you apply different inputs and see whether the output is correct or not. Let's assume you have written a function sum. Int sum, int a comma int b, and you say return a minus b. The output will be correct or incorrect? Incorrect. Logical error or syntax error? Syntax error. Or logical error? Logical error, because I want to find the sum and we are returning a minus b. Okay, so we apply different inputs to a and b and then we see that whether the function output is correct or incorrect. So there's the same thing. So how do we verify our logical circuit? By trying different set of inputs and see whether output is correct or incorrect. Okay, maybe we did some mistake in the algebraic manipulation and use wrong gates, and especially if I check majority of your quizzes, so majority of the answer will be incorrect. So then in that case, so you need to verify this thing. So we need to apply all of the possible combinations, all of these possible combinations. And can you see this is C plus D? So we are using C plus D here, and then B dot C plus D, and then we can say, okay, what are your all of the possible outputs. Okay, now this is an important topic. What now? This is another thing. Which step is this of the design process? Specification and specification. Please have your pen and papers. So now we are using some tasks. But before doing that, I will be going to explain the 7-segment display. Before solving, so first we need to understand what is a 7-segment display. And please, I need the attention of every student, because from each individual student I will ask some questions. I may ask from any student randomly, so I need your attention here. Okay, now what is a 7-segment display? A 7-segment display contains of 7 segment, which is called as LED. LED means light emitting diode. So now how many segment do we have? 7 segment. This segment is called as A, this segment is called as B, C, D, E, F and G. Okay, now we have 7 segment. Okay, assume that we want to display 1. So now we want to display a 1. Okay, so this is A, B, C, D, E, F and G. We want to display 1. B and C should be 1. So B is 1 and C is 1. B and C is 1. So this is B is 1 and C is 1. And all of the remaining are 0. Any question? Should you understand? Okay, now, yes, in the corner guy, I want to display 2. Which segment should be on? A, 2. A on, B on, G on, G, and then E, and then D. Got it? D on. And then all the remaining are zeros. What about 3? Okay. So now, if you look at here, what is the input? BCD. BCD, how many inputs? How many bits? 4 bits. So we have some, so we need to draw the truth table. So everyone please draw the truth table. So the input is BCD. How many possible combination? 16. How many outputs? 7. We have how many inputs? 4 inputs and 7. The truth table will contain how many rows and how many columns? Please just look at how many rows? 16. How many columns? 11. 4 for the inputs, 7 for the output. Everyone draw it. I'm coming to each and every student. Yes, please.